I don't know. Everyone is simultaneously.
All right, Yushuan, do you want to give a
Kind of a
My Wi-Fi is okay.
the Wi-Fi just returns to normal, so it's being streamed right now on YouTube.
I'll introduce myself.
Yeah, sure. Why not?
Everyone, my name is Yushan. I work with Mason on topological phases matter. And the presenter here today is Jing-Chen. Jing-Chen, say hi to everyone.
Hello.
He's working with Professor Hafezi, and he has a wide interest in almost every area of physics. I think you're doing an open quantum system right now, and Jing-Chen is gonna present scaling theory of conductance, which is a very beautiful theory at the 80s, 70s and 80s. And yeah, take it away.
Yeah. Okay. Thank you, Yushuan, for the nice introduction. Hello, everyone. Good afternoon. Sorry for the delay today because of some pizza issues. But fortunately, all of the audience right now are enjoying their pizza. So before I start, I'd like to say that our journal club talks are being streamed. So let's start today. So today I want to talk about the scaling theory of conductance, which was initiated by Wagner and these four authors in the 1980s. So Patrick Lee and the other author, they actually wrote a very nice review paper in 1985, and that paper was regarded as the start of the area of disordered electronic systems. All right, so today I want to start by reviewing some experimental methods in condensed matter systems. And by comparing the measurements of transport and the thermodynamics, I will introduce the universality in the transport measurements. And then with some intuitive pictures of conductance, I will introduce the main frame of the scaling theory of localization. And then I will briefly discuss the effect of interactions on the conductance. Finally, I will show one single experimental results that somehow confirms the scaling theory with 1D nanowire. All right. So in modern condensed matter physics, they're usually doing all these methods to do the measurements and explore new physics. For example, they can do some spectroscopy and measure the spectrum via different scattering methods. For example, neutron scattering. Or they can do some STM to measure the electron tunneling. Most importantly, or most frequently, they are doing some transport measurements that for a specific fabricated material, they can apply some voltage and measure the current and other responses. One famous example was the exploration of an integer quantum Hall effect, which Yushuan discussed a little bit in his first journal club talk. So we can see that if we apply some voltage on the sample, we can observe some plateaus increased by different integers. That's somehow very common in these days because topological materials are very popular in this field. However, today I want to talk about the other aspects of transport theory, which is more related to the thermodynamical measurements, where we can measure the heat capacity, magnetic susceptibility, or magnetization, where, as we have recalled in the statistical mechanics, if we have some phase transitions, then we can observe some peaks. And around that peaks, some thermodynamic variables may decay or increase by power law. And the exponent of that power law is only depending on the system and the dimension of the system, by which we call that's universal. The power law decay or power law increase, that was like the universal property of the phase transition.
Could you explain what is plotting?
So here we are plotting the heat capacity at constant pressure, and this is describing like a system undergoing the magnetization transition, during which it goes through the phase, the paramagnetic phase, or we don't have any net. This regime, or we have higher temperature. It's just like icing model. We don't have any magnetization, and when we sweep through the transition temperature, it goes to the magnetic phase, and here the peak of the heat capacitance is a signal of the phase transition. Yeah. Any more questions? Cool. So yeah, as I just said, today I want to show some aspects of transport measurements that's similar to the thermodynamic measurements. And we can see some universal features in the transport measurements as well. All right, so let's begin by some simple pictures from Ohm's law, which we have learned in high school or middle school, that the we can define the conductance of a material by the derivative of the current over the voltage. And for ohmic materials, we all know that it's just equal to the current divided by voltage. Also, is equal to the conductivity times the cross-section area divided by the length of the material. Okay, there is one simple picture of that description, but we're more familiar with resistivity. But here we're kind of talking about the same thing, but in the language of conductivity or conductance. So if this is a conductor with some cross-section areas and with some length 2L, then we know from Ohm's law that the total conductance of the whole material would be 1/2 of the conductance of the single piece of that material. Also, if we can split this conductor into n pieces, then we can have the same results, such that the total conductance is equal to 1/n conductance of a single piece. We can actually extend our results. And then what will happen? And this is exactly the essence of a renormalization group, that the system of a larger size is solely depending on the building blocks of that system. Meaning that the macroscopic observable is only a function of the elementary building block, which we will explain in a better detail in the next few slides. All right, any questions?
When does this fail?
When does this fail? That's a good one. I think when, as we will show in the later, in the later talk, if we have the L, the length of the scale is smaller than the mean free path of the electrons, then this will no longer hold, which means that this is no longer an ohmic material. All right.
I have a question.
Yes.
So when you say take L to 0,
Yes.
does that just mean take L as small as you can while?
Yes, correct. Yes. All right. Now let's review some of the basic definitions in the solid state physics. So we have, in the solid state physics, we have the density of states, which means that, which describe like how many states in a regime from the energy E to the E plus or minus delta E are located in that bin. We are familiar with the definition with extended states, and these are the states that we have non-zero density of states. The best example, these are the plane waves that we are very familiar with. So the wave function of that state is proportional to e to the ikx, which means that there are plane waves in the extended state. Also, we're familiar with the localized states, but in the definition of density of states, we refer to the localized states as the states when the density of states is suppressed, either exponentially suppressed or logarithmically suppressed or polynomially suppressed to 0 at some energy E. So the most commonly seen localized states are the wave functions are exponentially suppressed by the localization length lambda.
If it's polynomial suppressed, it never goes to the.
I think, but by that I mean like by that I mean minus like 1 over x squared or something. Yeah, it's not polynomially squared. It's yeah, algebraically suppressed, something like that. Yeah, and the most classic approach to describe either the extended states or the localized states is the Anderson model, which is very simple but very predictive and very physical. So here we have a Hamiltonian that describes that. So on a lattice, either 1D or 2D, we have the nearest neighbor hopping of electrons with strength T and some random potential on each side described by UI. If we can solve the energy spectrums of the Anderson model and solve its density of states, we can have the plots as below. So this plot is borrowed from Yuxuan. So as we can see from the plot, the y-axis is the density of states, the x-axis are the energies. So we can see that when energy is very small or very large, the density of states are suppressed to 0. Although it's hard to tell like whether it's exponentially suppressed or algebraically suppressed, but it's just suppressed somehow. Just by doing some simulation and see how localized the electrons are at these energies. Whereas in the center, we can see that the electrons have finite density states, and that corresponds to the localized regime. And there exists the edge that separates the localized states and extended states, and that's called the mobility edge.
Well, I thought when energy is on the side, then it's local.
Is what?
I thought on the center is extended, and on the side is local.
No.
Okay.
Yeah. And we can numerically find the mobility edge just by fitting this curve such that the localization length blows up. And the first energy when the localization length blows up was the location of the mobility edge. So that's kind of a formal definition for that. And here we're only talking about a single particle model, but for many particles, we can have many-body localizations. The definitions here mostly will apply into the MBL phenomena. But we use a different observable to characterize the localization, and that's called IPR, which is very directly measuring how localized a many-body state is. All right, so let's give some brief introductions of the main topic of today's talk. Let's show some basic property of the scaling functions. So to make things easier, we can make the conductance dimensionless because we want to see some universal properties. And we can define small g is equal to the large G divided by E squared over H. And note the E squared over H, that's essentially the units of conductivity. And that shows up everywhere. For example, in the integer quantum Hall effect, the conductivity will be some integer number of E squared over H. And also, if we completely forget about the quantum Hall or graphene and stuff like that, just consider the normal metal or some of the semiconductors, and we can measure the conductance fluctuation, and we gradually decrease the temperature. We will find that the conductance fluctuation at 0 temperature will always be some number to the order of E squared over H. That's called the universal conductance relation. You can actually check that from the paper by Patrick Lee and Douglas Stone in the paper of 1985. So yeah, this is also amazing. When people find it in the 1980s, they thought that was something there was something like miracle there, but it's actually calculatable. Yes.
What is conductance fluctuation?
Oh. Cool. So conductance fluctuation is that when we are measuring the conductance in different locations of the sample, we can write down the different conductance at different locations and average them. We can have like the average value of the conductance, right? And if we use the conductance, subtract the average value, and take a square, then that's the variance of the conductance. That's called the fluctuation. Yes, but here I mean just experimentally, that's how they measure. But yeah, you're right. From a partition function, you can do the same thing as well.
What is the energy scale here? Is it Fermi temperature or defect?
You mean the scale of that one? I think
When does it fail? Is it above Fermi temperature it fails, or above defect temperature, or is there some other?
I think the regime is when yeah, from my knowledge, it is at least true when it's at I think it's even below the Fermi temperature. It's essentially small.
Okay.
Yeah. So it's a fundamental property because of the quantum fluctuation. And yeah. All right. So you can recall our discussion from Ohm's law, and we can raise a key assumption to the theory of conductance scaling. that is we can assume that the conductance, the derivative of this conductance by the length is only a function of g alone, which and this in physics it means that the conductance of a larger material is only a function of the conductance of a single piece if we cut it in n pieces. And if you believe in that assumption, then we can get the derivative is called the beta of g, and the terminology is just borrowed from the RG theory, the beta function. Any questions? Yes.
How is this different from just having a material, assuming it to be ohmic?
So here we are saying that it's a function of g, but it's not necessarily a linear to g, right? If it is ohmic, then we will have some like simple proportionality, or there's at least a constant by that. But if we have like more complicated materials, then we'll probably have some like g squared or 1 over g dependence, and that's the coefficient in front of the functions, in front of the divisions of the conductance of a larger material over the smaller conductance. Yeah.
Okay, thanks.
Yeah, no problem. And yeah, just to recall that from Ohm's law, we can generalize the previous formula with cross-section area and length, just to think of some electron conductance from in a chunk of material with the size L to the D. And here you can see the conductance is very simple, has a very simple form. That's just sigma times L to the power of D minus 2. All right, then we're gonna explain some very simple but very powerful features of the beta function here. So here we have some physical parameters that will impact the validity of this whole theory, and that's these are the electron mean free path L, localization length lambda, and the system characteristic length L, which is usually like the size of your sample. Here we assume no electron Coulomb interactions at all, just for the simplicity of the theory. All right, let's think about what will happen if the system size is much greater than the electron mean free path. In that case, we can regard that scenario as the scenario when we have very low speed for the electrons. So when electrons are traveling in the chunk of materials, they scatter, right? They scatter and their phases will change. However, if your electron travels through like a very long distance, in the end, all of its phases will be averaged by the collisions from other electrons. So that's why we make that approximation. So this is all due to the phase randomization. Here we can here the model just returns to the simplest Jude model, and the system will be ohmic. Another limit is that what if the system size is much smaller than the electron free path? And we claim that electrons will be mostly localized, because when electrons wants to collide with other electrons, firstly, it doesn't go out of its localization length. So it's still localized before it collided with other electrons to get some more momentum. So we'll assume that its form will take up to the exponentially decaying around its position. So here it should be proportional instead of equal, to be more rigorous. All right, you may ask, what about the intermediate regime? In the intermediate regime, we claim that the scaling curve of beta versus G or L should be smoothly connected from the ohmic regime and the localized regime. And that is because if we only consider the disorder, usually for the mesoscopic system, they will change continuously with L, right? So if you don't consider any complicated constraints, your disorder strength will smoothly grow grow or decrease with respect to system size. Yeah, and another assumption that we make here is that we are assuming a monotonic function of the beta versus G, and that is so. This implies that G is proportional to the system size, right? That's kind of intuitive because when we have intuitively when we are growing the system size, the conductivity grows. So here that's sort of the assumption here. Yes. All right.
Quick question.
Yes.
So do these functions of G satisfy the assumption from the previous slide and that beta depends only on G?
Yes. Yes.
Okay.
Yes. So yeah, you will see
Oh,
later.
okay.
Yeah.
Yeah.
All right.
Sorry.
It's fine. So after that, we're going to explore some of the physical consequences. So if beta is greater than 0, the conductance will grow as the system size increase. And when L is very large, we call it in the thermodynamic limit. Then the system will be will grow to some number or to some infinity, very large number. Then we call it, we will see it's in the extended states. And on the opposite, if beta is smaller than 0, G will decrease as the system size increases. Then the system will be in the localized states, right? Because it decays to 0 or some, to 0 when our system size is very large. And when the beta function is 0, then there may exist at least one metal insulator phase transitions. But how many and how everything happens will depend on the details of the Hamiltonian. And this is exactly some of the consequences when we are doing RG in high energy physics or condensed matter physics, except for here, the beta function has a specific meaning in terms of conductance. All right, then we have this very famous plot. Let's just do some algebra and we can kind of work out the beta function for the ohmic state and localized states. Then immediately we find the ohmic states is very simple. It's as simple as some constant d minus 2, where d is the system dimension. In the localized states, it's just a logarithm of it's proportional to logarithm of g. Here gc is like a constant that indicates the phase transition. And based on that, we know some behaviors when g is very small, right, on this end. And note that here the x-axis is in the log scale, it's in log g. So when g is very small, then log g is very small. Everything is on this end. It should be some logarithm function in this limit. And when g is very large, we go to the ohmic limit. Then for d is equal to 1, that is here below the x-axis. When d is equal to 2, it's exactly 0. When d is equal to 3, then we'll have something on the top that's equal to 1. So we can get some simple but powerful results that coincides with the previous research. That is, in 1D, all states are localized. So that has been verified a lot of times in the theory of Lagrange liquid, or in the theory of basic solid-state physics, or most, or you can check the first paper that describes this phenomenon by Mott and Dwals in 1961. Another important implication is that in 3D, there exists at least one metal insulator transition, and that corresponds to the behavior of most metals, like in terms of metals or liquids, in terms of 3D samples. And in 2D, we call that the system is marginal. That's because the beta function is exactly 0, and it's very sensitive to the perturbations when G is large. So we call it marginal, because any kind of interactions, relevant interactions, may change the curve of the beta function in 2D, such that there may be some bumps right here that causes some metal insulator transitions. All right, so if you have learned RG, you may ask, this just looks like the formalism of RG, but why can you do so? Is it valid to just borrow the tools from RG and carry on the calculations? There's actually some physical evidence and some physical motivations, and that's firstly came up by Wagner in 1976, and that is based on some experimental results. The conductivity is universal when we have very low temperatures near a metal insulator transition, and that is the conductivity is power law suppressed to some universal component mu. So EC is the number of is the value of mobility edge that we described in the previous few slides. So Wagner actually just from this observation, he came up with some perturbation theory using the language of RG. However, there are fundamental differences between the usual RG and this scaling theory of conductance, and that's because in our theory of conductance, we have like more constraints when G is much smaller than 1 and much greater than 1, and that kind of restricts our RG phase diagram comparing to the usual formalism. Any questions? All right, I'll talk more about it when we go into the end. All right, so you may ask, what about the interactions? We know that in condensed matter theory, there are different kinds of interactions, like spin orbital coupling, or some magnetic field, or some different spin-spin interactions. And in order to make everything work, we have to use some microscopic theory, and that's called Kubo formula. And Kubo formula is nothing but to compute the conductivity by computing the two particle Green's functions near the Fermi level. And usually when we're talking about the Green's function, we're talking about a lot of diagrammatics, and we kind of use different techniques to get some valid results. So I won't talk about the details, but just to show you that we can actually compute the conductivity relatively accurate, at least quantitatively. Yeah, one important thing to notice is that the above formalism is based on the it is only promised working in the perturbative regime, and that is the Fermi momentum times the electron mean free path is much greater than 1. let me give you a brief example of the effect of interactions. So if we only have some electron backscattering, which is more common than the topological phenomenon that electrons will just go through the disorders without backscattering in most of the metals. If we consider the backscattering effect, there will be an extra factor A divided by G. So you can see that this part is non-trivial function of G, right? In contrast to the trivial ones of the ohmic and the localized case. And this serves as the effect of like kind of shifting the curve downwards. But if we have some more complicated function of G in the perturbations, then we'll probably have more ripples in 3D or in 2D, and therefore there may be more fascinating phenomena produced by our diagram. Any questions? All right. So in the last part, I want to connect the scaling of conductance to the experiment. And in order to connect it with the experiment, it's usually better to vary the temperature, because that's usually a continuous variable, rather than continuously vary the size of the sample, because you only fabricate like one sample with a specific size at a time. And we can, if we assume that the lifetime of the electrons satisfy the parallel decay relation with respect to the temperature, and that means physically we only have the screening between electrons and completely forget about the Coulomb interactions. Because if we have Coulomb interactions, then there should be a exponentially decaying part in addition to the parallel decaying contribution. And then we can define the thermal length, and that's also parallel decay. If we put that thermal length as the lower cutoff for the conductivity, then we can find some similar universal scaling relations for the conductance. And so for 3D, that's some parallel with positive exponent, and for 1D, that's also like parallel relation, but with negative components. And for 2D, that's marginal, so it's logarithm scaling. All right, and then we can actually see some actual experiments. So here in the group of Andrei Kritinin in 2011, they are kind of using a sample of indium arsenide. Sorry, I think I made a typo right there. So it is indium arsenide, and so that is essentially a nanowire that's lifted between the two silicons.
That bar is 1 micron.
That bar is 1 micron. Yeah. Okay. Yeah. And then they kind of do the experiment to measure the conductance, and they want to see how the conductance measured is comparable to the predicted universal scaling of conductance. So the main results are shown in the picture A and B on the right. The red ones are the red and the blue ones are the experimental data. The black dashed line are the predicted curve using the universal relation. And we can see that when the temperature is very low, they coincide pretty nicely with the theory. So that's sort of an evidence of the universal scaling of conductance.
Back to the previous one.
This one?
Okay.
Yeah.
Yeah.
All right. All right. So at last, I want to discuss some open questions. From my opinion, I think it is a very beautiful theory of the universal scaling of conductance. However, as I was doing the literature search, I kind of questioned the validity of this relation in strongly correlated materials. Maybe there are more experiments needed to further verify this relation. And also, I find very few literatures talking about the conductance scaling in open quantum systems, which is something I'm mostly interested in. And that is when we are adding some laser driving on your sample, or if we can engineer the dissipation, what will the conductance be? Will it still be universal or not? The third part is the connection with the Thibault-Zurich mechanism. So Thibault-Zurich mechanism is a mechanism that computes quantitatively the size growth of the topological defects near a spontaneous symmetry breaking. So it predicts that the size of the topological defects will grow in parallel with some exponent, and that exponent is related to your type of spontaneous symmetry breaking, which is
growing parallel. What parameter are you taking?
we are just we can tune, for example, the size of it's whatever the order parameter you're causing the phase transition. Yeah, for example, the magnetic field or some interaction strength, and the different exponents is depending on the details of your symmetry breaking and the universality before and after the symmetry breaking. So one may ask a question: what about the conductance? Can we apply some of the methods in Thibault-Zurich to compute the conductance very easily? And this is actually related to the last question, and that is, can we extract different phases from the universality class? I should put some quotes here, because I don't know much about the actual universality class, because it's still very debatable in the recent papers. So the last question is actually, can we extract some universal properties from the universality classes that participates in the conductance? Say, can we draw more complicated diagram of beta function versus G? And can we have some Wilson-Fisher fixed points or some other interesting RG phenomena in the diagram of our conductance? Yeah, all these questions are kind of under research. All right, I think that's all the materials I want to cover today. I'm open to any questions right now.
What would be the order parameter?
This one?
Yeah.
This one, it depends. I think it depends on the systems, right?
Okay.
If you can actually do two things. Firstly, you can go back to our curve. Yeah. So if you can refer to the G as some order parameter, and or you can kind of actually induce some phase transitions and plot different curves just in different parameter regimes. For example, this happens in the paramagnetic phase, However, in the ferromagnetic phase, this curve may become some rippled curve that leads to a different fixed points in the when G goes to -infinity, something like that. So yeah, it depends on how you draw the diagram. Yeah. Any more questions? All right. So if
I have a question.
yes,
Mu is universal with respect to the details. What details specifically? Like the details of the metal? I mean, is it universal in terms of all physics? Isn't that just
yeah.
about-
So it's universal in terms of, for example, the percentage of the impurity.
Oh, okay.
Yeah. For example, this can be mu can be 0.2 of the percent of the impurity, and it's universal because it works for both the gold and silver, with different types of materials, as long as the percentage is the same and the size is the same, then you will find similar results.
Okay.
Any more questions?
So that should be the same number. That should be a fixed number.
Yeah, that should be a fixed number just for some for a single class of materials, I think.
What I mean is that shouldn't depend on a fine parameter that you can tune. For example, the defect density, right?
I think here is it's very vaguely. It's just a percentage. I think the percentage is
So that is different from the particle exponent.
yes, that's not the
Uh,
yeah. So it's universal in a different sense than the usual Ising model. Yeah. Any more questions? All right. If there are no more questions, I want to thank you for all being here for the talk. Yeah, I'll see you in the future.
Thank you.